All right, so welcome. I'm gonna give you a brief update on GigaIO, and I'm gonna start with a handful of slides about the company and the technology, and then we're gonna talk about the results of testing that we've done in San Diego. Can you hear me? Hold it closer? All right. So we're going to talk a little bit about the company and the technology, and then we'll go into some of the specific testing that we've been doing with San Diego Super. So first off, we have all the pieces of the interconnect itself. All right, so a traditional top of rack type switch, the resource boxes that plug into that, the cards that go into the servers, the cabling, and a lot of software that runs on top. And we're focused on the advanced scale market. So if a individual can run their entire job inside one server, they don't need what we do. But if they need more than one, if it's more than one server, if it's storage and accelerators and so on, then our I/O is the perfect thing for them. And effectively, it's about changing the paradigm of the system. So instead of having a rack of servers with a variety of resources that are inside of those servers, you can now disaggregate that rack, and you can put CPUs, you can put accelerators, you can put storage into their own boxes. And as you decide that you want to change a given element, you pick up the box and you change it. You don't have to open up the box. You don't have to change the operating system. You don't have to reconfigure a server. So you don't have everything in the server or in the rack on the same obsolescence and upgrade path. You can put them all on their own paths. And basically the basis of the advantage, if you look at server 1 and you look at server 2, the output of those chips, right, whether it's an Intel chip or an ARM chip or an AMD chip or a Power 9, the native language that's coming out of that chip is PCI Express. And the architecture inside of that server, pretty much independent of who it comes from, is also PCI Express. And today, if you're going across an Ethernet network, or you're going across an InfiniBand network, or a fiber channel network, you are coming across PCI in that server, you're translating into InfiniBand, you're moving across their network, and then in the second server, you are immediately converting back to PCI. And quite simply, what we've done at GigaIO is we figured out how to use PCI Express as the basis of a true multi-host network. And so you get tremendous performance advantages, and secondly, you get a capability of being able to scale up and out on the exact same infrastructure. So you can scale up the capabilities of a given server, and then you can scale it out on the same exact infrastructure. And so architecturally, right, what we have done is we have implemented inside of our switch effectively the master root complex for the entire fabric. So the servers themselves have a root complex, they enumerate their devices, and then on our server in the software, we create what we call a master root complex, and then we enumerate all the resources that happen there in the fabric. And so what it gives us now is the capability of doing what you would expect. You can do server-to-server communication. We can run MPI applications. We can run TCP/IP emulations. We can run InfiniBand emulations. And you can hook up to storage appliances and storage servers and other servers, so you can run NVMe-OF, you can run GDR, right? So you're running these multi-host capability, but you can also attach resource boxes. You can attach JBOFs and JBOGs and attach storage and accelerators of all types into the fabric. And because it's PCI, you can actually run memory semantics on this fabric today. So you can do loads and stores across the fabric. So you don't have to do reads and writes. You can do a load and store, a true memory semantic load and store. Okay, so with that in mind then, let's talk about some of the testing work that we've done with San Diego. We've been running 2 tests lately. The first test was really just about benchmarking, and we did some fairly simple benchmark tests initially. So we were running some P2P programs and some memory bandwidth. Then we moved into some more difficult, we went into Monte Carlo analysis. And then this package is it's a seismic analysis package that San Diego Super has run, and they've written that package, and so they wanted to see what this would do across the fabric. And then the last one we wanted to compare against a very interesting large-scale system that's there. So in summary, and then I'll show you the detail behind this, is Ron initially said, emulate, so we've got our Comet system, and so effectively, emulate in your architecture 2 of our nodes, right, on our system, and 2 of their nodes at list price is about $140,000. And so using our fabric, we created what we thought was going to be equal performance for about $64,000. And it turns out that we overshot. We didn't get equal performance. We actually get about 25% higher performance for roughly 1/3 of the price. All right, so here's the 2 configurations. So you can see right off the bat that the architectures start to look different. So in the Comet nodes, a very standard dual processor system, 2 GPUs per processor, 4 in the system itself, connected together with InfiniBand, about $140,000, okay? Using FabreX, you can see the architecture ends up looking very different, right? So in this case, we were running 1 very skinny server. So this was a 1 single processor server with a relatively small amount of memory. 12 GPUs that were attached into the fabric. That, by the way, they can be attached to 1 server in 1 instance and then another server in a second one. And we attach storage directly into the same fabric. So I'm just going to run you through the tests pretty quickly as to what we were actually finding from a benchmark perspective. So on simple P2P, right, it's bandwidth, and you can see higher is better in this case, and so Rincon is our system. Comet, of course, was the existing system. So we were doing slightly better on the simple P2P transfers. In the memory, in just a straight memory bandwidth testing, you can see the Comet was actually doing a bit better. All right, so this is one where the Comet system was looking better. And in the Monte Carlo, now in the Monte Carlo, the lower number, this is the time to solve, so a lower number is better. And you can see we actually did quite a bit better in the strong scalability and even better in the weak scalability. And it's because now those 12 GPUs across our fabric are actually very efficient. And we'll come back and I'll show you the number here in a second. So if you look at the strong scalability, and this is the interesting one to look. So look at it, the efficiency versus the ideal. So with 1 GPU, of course, you're going to get 100% capability. But in the existing Comet system and across InfiniBand, the efficiency of the GPUs falls off very quickly. And so as you start adding more GPUs into that system, the effectiveness, your ability to drive those GPUs starts to decline rather dramatically. And across a full speed, full efficient PCI fabric, that doesn't happen. And you can see we're taking much better care of the GPUs. And the same is true in the weak scale testing, right, where we're just getting more efficiency out of the GPUs. You spend a lot of money on the GPUs. They're not cheap, and so it makes a lot of sense to get the best use out of them. And then this was sort of fun against the SGI system, because this is a really expensive SGI system. And you can see from a bandwidth standpoint, we did considerably better. And again, remember, it's a $62,000 system. All right, so this was just a fun test to do. So the folks at SDSC, the research scientist Dawei Mu presented his paper and talked about the results that he had gotten. And then just recently, we've been working with him on a second project where now, again, using that one CPU, he wanted to be able to do both compute and visualization at the same time. So he wanted to be able to do them concurrently. And so what he was able to do was to be able to assign a certain number of GPUs to run the compute part of his seismic analysis. And then at the same time, he wanted to be able to take the output of the compute and put them right into a visualization part. So a handful of GPUs doing compute, and then a handful of GPUs doing the visualization at the same time. And so running across the fabric, he was able to take that message out, split that job up across those GPUs. Now, in this particular presentation, I don't have the running version of this, right? But he shows the video where he's actually doing the compute in real time, and you can actually watch the waveform, right, progress across the screen. And in this particular data set, this is actually the volcanoes, the Hawaii volcanoes that just the ones that recently erupted. And so he was taking seismic analysis off of that package. Oh, actually, I do have it, and you can notice you can watch the waveforms advancing, and he was able to watch the compute happen at the same time that he can see the visualization, and that was by assigning, once again, he assigned the jobs to different sets of GPUs across the fabric. So the next steps now is now to overlap the I/O and start to run MPI. So our MPI drivers are up and running. We've written our own libfabric providers for this network. MPitch is running on top of that. And so he's going to start taking advantage to run his MPI application across multiple servers. That, by the way, is up and running, and it's at this show back in the student competition, right? There is one of the universities that's got our hardware up and running. They've got 3 servers. They've got 8 GPUs, and they're running MPI applications across the fabric. So we've had a great relationship with San Diego Super. They've been big supporters, and we certainly intend that we will continue that relationship. And we've mapped out more projects to come. And with that, that's us. So if there's any questions? All right, so we're around. If you have questions, just stop by.
Why did you use the GTXs instead of comparing with the V100s? Is that just what you had?
So his question was, why did we use the 1080 Ti's, the GTXs, as opposed to the V100s? And he said, was it just because that's what you had? And yes, as a startup company, that's what we had. What's interesting, in the student competition here, they do have the V100s, right? NVIDIA was nice enough to donate the V100. So V100's running the fabric with no problem. It is interesting to be able to see. One of the things that we can do with the fabric is we can expand to much greater numbers on a given CPU than what could be done with having to shove them into a box. So what we do find is that there is, I would say NVIDIA's cost curve is not linear. And so we can put together a large number of less powerful GPUs at a far lower cost. But, but the V100, it doesn't matter. The V100s work fine, right? And as the 1080s did as well.
One other question. Can you orchestrate the number of GPUs that you have connected into any one system? So you could have composable infrastructure
So his question was, can we orchestrate the number of GPUs and effectively be able to partition them to other servers? And the answer is yes, right? So depending upon, you can either do it in, I'll call it a relatively crude way, depending upon the number of output ports that you have on your resource box. And on our resource box, we have 2 ports, so you can put them on 2 systems, and then you can move them around. Or with GDR, you can actually, because we can do server to server, so we can treat it as a compute server, and you can actually do some much more granular sharing, right, at much smaller detail than that. Okay? Very good, thank you.